Okay, good morning, people. As I see, not many have logged into this morning. We'll give a minute or so for others to log in. We have a count which is nearly half of what is expected. So I'm not sure if people are back from the long holy holiday, weekend. But we'll give a minute or so for maybe others to join in. Okay, meanwhile, let me just pose a small question to you who have who have been humble enough to nice enough to come at 10 this morning. The thing is, we are on to our 14th. I think today is our 14th class. It's probably the second last class of our interaction. Now, our interaction has been twice a week. I'm not sure how does your college or university work, but over here we have 3 hours of interaction per week. So assuming that if you have 3 hours at your end, so there is 1 extra hour each week, and I would like to know what you have been doing on that hour. So I have a list of all the colleges who have been associated with this course. So the list of colleges and universities are with me. The thing is, I need your feedback. Feedback on few things. The first one is, of course, like I said, the 1 hour which you have spent, 1 hour what you have been doing. So the feedback can be from the teachers and from the students. So from each university or institute, I expect a lot of feedback. Each email coming into me. So you can drop in an email to me. I have given the email ID towards the early part of my lecture. I hope you still have it and have not really thrown away that piece of paper. The second feedback which I would very much appreciate is the quality of the coursework or the quality of instructions which have been given to you. So that is the second feedback which I would appreciate. The third feedback, which I think is a more general thing about the overall program. How would you rate this overall program? So initially, we had figured that maybe we can do this among the live session. I click on a video, so either you come onto video and we start this interaction. But I'm afraid the 15-hour contact program had been pretty tight for all of us, and I would have to skip this live feedback, meaning you going on live and then giving me the feedback, so that it helps others as well. But because of this, I would appreciate that you just give a feedback on your via email. Please do this thing. I have the email, the university name of all the colleges, and if no feedback comes, I would report this. Believe me, I would report this. So please do send a feedback. Thank you. So I'll continue with today's class. We still have a smaller count. I hope people will join in as we progress with our today's class. Today's class is on shear strength. It's a rather interesting but a very long topic, and it possibly will not be able to. We will not be able to conclude in today's hour or the hour later this part of the week. But I tend to cover up at least the major chunk, so that when you go back home and you refer to any textbook, you are comfortable on this chapter. Okay, I say chapter. There are a few subtopics which I intend to complete today. The first one is what is stress at a point. So if you have a material and you load a material, so by number of stress pressure points, and you are interested in what is the stress on that material and within a point. The second thing we'll cover up is perhaps the difference between failure and yield. In between, we'll do a small problem, and if given a chance, we will give a small introduction to Mohr Coulomb strength. Okay, so let's begin. I have a small sketch, a cartoon at the top right figure. Please look at the top right figure. I hope it is visible. If not, it just shows a small bob on a part of an element. Usually when we look at an element, we say it's continuum, meaning it's continuous. So assume that this is a part of a continuous element which is subjected to a number of forces from all around. Okay, and our first subject of interest is what are the normal and shear stress on this point O. In usual convention, when we need to deduce a normal and shear stress on this point O, what we say is we look at a small element. So within the large mass, we are looking at a small element, and by virtue of convention, the element is either represented as a square or a rectangle, anything which a regular sided figure. So what I have is an element, a rectangle over here, and I assume a rectangle to be somewhat like this. Let me see if I can draw. Oops. So that would be okay, thank you. So I presume that is my element. Okay, so I have just completed the element. It's more of a rectangle. That element has been extracted from O, and we are interested in is what are the resultant of all the forces which you apply. Now usually when you apply forces in all directions, basic elementary physics tells us we can resolve in 3 directions. So normal to this, the other normal, and the third normal which comes out and hits you. So the three directions which you're looking at. And all the 3 forces in 3 directions, if they are resolved, let's call them as horizontal H and vertical V. So I have a horizontal H over here and a vertical V. If I want to look at the third direction, of course we are not looking, we are just looking at 2-dimensional figure just to simplify our case. So if you're looking at just 1/2 of this element, which is at O over here, and our interest is what is the normal force and the shear force. Remember, shear force is sliding. So what is the normal force and shear force on this element? If you look at this carefully, if I look at just the bottom half, this plane is, I say, is an incline at alpha. So our interest is on a plane which is at an alpha, and if I assume for the time being this inclined surface which is over here, let me just redraw over here. This inclined surface, I'm not sure if I can get a different color, but that's black color for me. Black color, right? So no choice of color. This is the line which I'm looking at. I'm looking at normal and shear force, and the area, I say it's 1 unit area. That's area equals to 1. If this is 1 and alpha being the angle, elementary trigonometry tells me that the bottom line has an area of 1 cos alpha. Likewise, the vertical line has an area of 1 sin alpha. Okay, elementary trigonometry. If I say this is the horizontal force, and I say the stress, the horizontal equivalent stress would be sigma 3. So the horizontal force would be sigma 3 times the area. So I have sigma 3 times this area, which is 1 sin alpha, or sigma 3 times sin alpha. Likewise, the vertical one would be sigma 1, and the area is cos alpha. Okay. The next point I need to emphasize is the sign convention we follow. The sign convention we follow is, in soil mechanics, the sign convention is slightly different than what we follow in structural mechanics. In soil mechanics, any force, any traction, any stress which causes compression is taken as positive. Okay, so squeezing in of a material, of a soil mass or the soil element is considered to be positive. So compressive forces are taken to be positive. The second thing is, what about shear forces or shear stresses? If I'm looking at a shear stress along a plane, for example this plane over here, and if I look at the direction, in this case the direction is shown upward. Okay, if I take a point just outside this plane, for example this point which is shown over here as a dot, this dot over here, if I take a rotation of this arrow above the dot. Remember, this arrow points upwards, so this point is outside the element, meaning outside the lower half of the element which is of interest to me. I'm looking at shear forces on this lower half. So that's a lower half. Apologize for this figure, but it's still a rectangle for us, So this point rotation is clockwise rotation. So in case the shear stresses induce clockwise rotation about a point which is just outside the plane, okay, then the shear stresses are considered to be positive. So in this figure, the arrow being upward, I can safely say the shear stress is positive. Okay, let me go to the next figure. So if I'm going to concentrate on this small caption on the next slide. It's the same caption, the figure has been slightly zoomed in. Okay, again, if I take the sum of all the horizontal forces and sum of all the vertical forces and equate them to 0, meaning I assume that there is no rotation or translation of this element. This is what we assume, that there is no rotation or translation of this element. In other words, sum of horizontal forces sigma Fh is 0 and sum of vertical forces sigma Fy equals to 0. So I can say this H, which is the horizontal force, minus T cos alpha, which is say second element. T is the shear force along this plane, and cos alpha, I resolve this in the horizontal direction, so it's cos alpha. Similarly, N is the vertical normal to this plane. If I want a vertical one over here, I get N sin alpha. I'm sorry, I'm looking at horizontal. Horizontal would be N sin alpha. Vertical is N cos alpha. I'm looking at equivalent to or sum of horizontal forces. So I have H, horizontal component of this normal will be N sin alpha. Similarly, the horizontal component of the shear would be T cos alpha. That's the first one. Likewise, I can equate the sum of vertical forces to be 0. Okay, I'm not going to run into this, but you're looking at this figure will help you to look at, visualize with vertical is V plus T sin alpha minus N cos alpha, that equals to 0. So H and V are horizontal and vertical. I have just replaced this by the stress times area. Similar, T is the force. I replaced this by T is the shear stress, but because it acts on the unit area, so I have tau. Tau equals to T times 1 because the area is unit area. So I have just replaced T by tau. Likewise, N is the normal stress, normal force. I apologize again. Normal force on this plane. So if I convert this into stress, it will be sigma times 1 because this is 1 unit area. Okay. Likewise, the second expression over here will give me the in terms of stresses, shear stresses and normal stresses. If I solve these two equations, okay, what I have is, if I solve these two equations, I have the first one, which is sigma. In terms of sigma, that is the normal stress on this plane. Sigma is the normal stress on this plane, is equals to sigma 1 plus sigma 3 by 2 plus sigma 1 minus sigma 3 by 2 cos 2 alpha. Okay, this is an important expression. Again, it's very useful in case you go back home and if you look at the derivation, this equation has a very simple derivation. If you're still uncomfortable with the derivation, I suggest that you take this as a tablet, but nonetheless, please go back home and look at the derivation again. The second expression which I will have, you remember these two are two equations with two unknowns. First unknown is tau, the second unknown is sigma. I have just solved or written the equation for sigma. Likewise for tau, you can have an expression for tau equals to again sigma 1 minus sigma 3 by 2 times sin 2 alpha. Now over here I would like to emphasize that these two expressions, in these two expressions you have sigma 3 we took it as a horizontal stress and sigma 1 we took it as a vertical stress. We purposely took this because this is the convention we use in soil mechanics. Sigma 3 is the we take it as a horizontal stress, likewise sigma 1 to be vertical stress. Okay. Let me move on to the next slide, please. Those two equations we have in terms of sigma and tau, they are the expressions or the solutions, meaning if I square them up and okay, and add these two, it leads to an equation of a circle which has a radius of sigma 1 minus sigma 3 by 2, and this circle will have a center as sigma 1 plus sigma 3 by 2. Let me just look at the next slide, it will help me. That's the circle. Remember, we just said the equation of the circle with two ends, meaning the center of the circle, if you look at this circle, sigma 1 is over there, sigma 3 is this end over here. The center of the circle would be sigma 1 plus sigma 3 by 2. That's the center. What about the radius? The radius would be sigma 1 minus sigma 3 by 2. That's the radius. Okay. Now this circle is called as Mohr circle. It represents the stress state of the element at any plane. Okay, I can deduce the stress state of the previous element. Remember, we took an element around the point and we drew a rectangle or a square, any figure you're comfortable with, and with that figure we said the two stress, that is sigma and tau, were one particular solution, and we said this solution, you can generalize the solution using this Mohr circle. Okay. We are looking at this circle, and the bottom line of this circle, I repeat, is you can deduce sigma and tau at any plane. Okay, at any plane within the element, and in the next few slides I'm going to explain this how. Before that, we look at this element again. This time, of course, it's a longer rectangle. Again, my shape of my rectangle has changed, but it still represents an element. Okay, wherein the sigma 1 is the vertical stress, sigma 3 is the horizontal stress, and in this element I have conveniently assumed that sigma 1 is bigger than sigma 3. If sigma 1 is bigger than sigma 3, sigma 1 will be here because it's of larger magnitude, sigma 3 is there, and with these two ends I draw a circle. Okay, so I know the diameter, I can draw a circle, it's easy for me. Once I draw the circle, the previous slides told me that I can deduce stress at any plane. At any plane alpha, in the previous case we had a plane at alpha, so we can deduce at any plane with any value of alpha. But you need to know one point, and that point is called as pole. This slide over here will explain what is pole. I would like you to run the first three lines very slowly. Okay, the first line says pole is a unique point. Unique point would mean if I have this circle over here, this pole would be one single point, irrespective of what plane you are looking at. The point is unique. It will not change. So it's a unique point on this Mohr circle, such that any straight line, any line, so for example, if I say this is my pole over here, okay, that is my pole, apologize, black color not very visible. I think I can use a highlighter. Highlighter is equally bad, but that's my point over there. So the line continues to say, if I draw any straight line from this point, meaning here, oops, who used the most? Where's the undo, please? Okay, it's all gone. So that is the point over here, and if I draw a line from this point, meaning I draw over here a straight line, apologize for these curvy lines. If I draw any line from there and it hits the circle at the other end, either there, in this case it hits the circle here and there, meaning these 2 points, the coordinates of these 2 points would be x coordinate would be sigma, the y coordinate would be tau. So the coordinate sigma tau over here, sigma tau over there will be the normal stress and the shear stress, okay, on a plane which is inclined to this same angle, which has the same angle as this plane or the same angle as this plane. Okay, so pole is a unique point on the circle such that any straight line drawn through the pole intersects the circle. So this intersection over there, okay, intersection over there, or intersection over here, anywhere, intersects the circle at a point which represents the stress state, meaning xy coordinate on the plane. That's the plane, that's the plane, that's the plane, which is inclined to the same orientation as the line. So if the coordinates of this point over here will be the normal stress and the shear stress on a plane which is inclined to this angle. Okay, so if I erase these lines, let me see if I can erase. Yes, it's gone. And if I say these two are two stresses on the element, remember there would be an equally opposite over here. There would be some over here which balances sigma 3, one stress over there which balances sigma 1. I have not drawn this, okay, but it's, of course, it's assumed that these two stresses are there. That is why there is no rotation or translation of the element. So if I erase this again, can you look at this figure and then, judging from the first three lines, tell me where is the pole? That's the circle. Where would the pole be? Okay, can you please estimate where is the pole for this stress state? Remember, sigma 1 is bigger than sigma 3, so I have drawn sigma 1 over here. Can you estimate where is the pole? Right? Let's look at this sigma 1. The coordinates on this plane, that's the plane. The coordinates on this plane are sigma 1, which we say is the x coordinate, and the y coordinate is tau, which is 0. There is no tau on this plane. Okay. Likewise, if I draw a number of planes which are parallel to this, okay, apologize for the second line, but all these are parallel lines. Okay, I'm drawing using a mouse, but I hope you can visualize all planes parallel to these planes, meaning I can have millions and zillions of planes. All these planes will have a normal stress which is sigma 1 and shear stress which is 0. Okay, let me erase this again. So normal stress sigma 1, shear stress 0. So that's the coordinate over here. X coordinate is sigma 1, y coordinate is 0. Okay, so if I look at this carefully, that is my coordinate. And by virtue of definition of pole, a line which starts from the pole and is at the same angle as this plane is horizontal. So if I draw a line which is horizontal, meaning ending at this point, if I draw a line which starts from here, okay, it starts from here, ends over there, this coordinate is the sigma 1 tau. In other words, if I draw a line which has termination over here, it will start from somewhere, I go back, that's the starting point, meaning this point over here is the pole. Okay, if I want to look at the other stress, the vertical stress or the x coordinate on this plane is sigma 3. What is the y coordinate? Y coordinate shear stress is 0. In other words, this is the point over there, like we said, sigma 3 is over here and y is 0, shear stress is 0. So that's the point. So the stress on this plane are xy, and if I draw a plane which is parallel to this, meaning it's straight up and down, that's the parallel over there, it should start from the pole. Now it only intersects the circle at this point, meaning that point itself is the pole. So if I rephrase my last few statements, irrespective of you looking at the stress state over here or there, the pole is still here. Okay, it does not matter. If you're still slightly confused on this, not to worry, we'll do a problem. We'll do a problem and then exemplify this situation. That is the pole shown by yellow dot. Okay, I think the problem is listed in the next few slides. Before that, let's summarize these few statements. We say on the planes where there are no shear stresses, meaning no shear stresses, when tau is 0. When tau is 0, those planes are called as principal planes, and the stresses on the planes are called as principal stresses. So if I go back, okay, that's the horizontal plane, there are no shear stress, so this plane is principal plane, and that's the principal stress. This is again a principal plane, and that's a principal stress. This, of course, being bigger than the other one, I'll call this as a major principal stress, and this as the minor principal stress. Okay, there is a third stress, sigma 2, which is intermediate. Remember, we have just done sigma 1 and 3. There is a third stress, sigma 2, which is the intermediate, and we tend to ignore because it lies in between these two, and the theory, most of the theory which we will study on the shear stress or normal stress tend to only utilize sigma 1, sigma 3, assuming that sigma 2 lies in between these two, meaning our stress state is dictated by the major and the minor principal stress. Okay, so that's the figure over there. So this again means that's the one principal plane, that's the other principal plane. Likewise, I can draw millions and zillions of vertical lines. That will, all these lines will be minor principal planes, and horizontal lines would be, all the horizontal lines would be major principal planes. There are other important things to remember when we look at the shear strength. Remember, we are just doing an introduction to shear strength. The first one is volumetric strains. In order to understand volumetric strains, take a small element, and if I try to squeeze this element from all around, meaning I squeeze this with equal pressure from all around, no equal pressure all around. In such a case, it's called as pure volumetric compression. So under pure volumetric compression, the element does squeeze in. There is squeezing of the element, okay, but this element will never fail. It is of surprise to us that the element which is squeezed in will undergo volume change, but there will be no development of shear stresses. Okay, now the question is why? Okay, let's look at the equation which we had derived earlier. Let's go back a few slides just to explain this. Okay, that's the equation over there, and if I can zoom in, okay, that's the equation. So this expression gives me the shear stress tau. If I squeeze this element from equal pressure all around, the stresses are equal. Remember, sigma 1 would be the same as sigma 3 if I look at an element which is 2D. In other words, tau equals to 0. There are no shear stresses. However, the element will squeeze in. So there would be, it would undergo volume change, but it will not squeeze in. So if I go back to our current slide, it says volume will change, but volumetric strains will occur, but shear strains, which is because of the shear stresses, will not occur. Okay, so volume strains will occur, but shear stresses will not, or shear stresses or shear strains will not occur. That's the statement over here. Soil will fail only when shear strains or shear stresses exceed some value. Okay, so if these two are 0, soil does not fail. If you are, if you look at an odometer test which we did, odometer's test, that was your sample, and we squeezed the sample from the top by reaction. It was being squeezed from the top bottom, and we had this confinement from all around. Okay, the cell did not allow the soil, cake of soil to laterally deform. So in this case as well, we had volumetric strains. There were some shear strains, but the shear strains never exceeded this value, never exceeded a certain value. That is why when you did an odometer test, you could squeeze in the soil element by putting in as much as load as you want. You could have put as much as load, but the soil will never fail. It will only undergo squeezing in. Okay. So these two, of course, we'll next week, next class, we'll get an opportunity to really look at this in detail. Now, I have a small problem over here. In fact, I have lined up two problems for the next 25 minutes, just to explain what is pole. Okay, remember today's class is an introduction to shear strength, and understanding of pole is important. And I would like you to look at this question. This question is there on your slide. You can download this by right clicking. It's the same part of the same PPT. Okay, please go through this question. The first question, please. For the benefit of those who logged in slightly late, I have made a request about feedback. Please, I need your feedback via email. Please send it to me. Okay, this question shows us is an element. This is again an element. Normal stress sigma 1 and sigma 3 act on this. Remember, there are no shear stresses on this plane as well as the other plane. This stress as well as the other stress are the principal stresses. Of course, this being bigger than the other one, this is a major principal stress, that is a minor principal stress. The question is, if the element is rotated by 20 degrees, you are asked to find out what is the normal stress, what is the normal stress and the shear stress, okay, sorry, on this plane. Okay, it does not matter if I look at the upper half of the element or the lower half. Upper half and lower half, the sign convention of normal stress will be the same. Only the sign convention of shear stress, you have to be careful. Okay, it will be the same, but you have to be careful in which direction you need to draw. Let's look at this solution to this problem. Okay, for this solution, the best bet is to first start off with the scale. You know, that's the vertical stress and the now horizontal stress. By virtue of horizontal stress, we call this as the normal stress, and the vertical axis or the vertical stress, we call this as the shear stress. That is the one. Remember, to begin with, we cannot measure shear stress. Okay, this cannot be measured. Okay, we cannot measure this. We only measure sigma. So that is why all our drawing, plotting is along the horizontal axis. So if this is the normal and that's the shear, I can draw the first one, sigma 1. If you look at the question carefully, sigma 1 had a value of, I think, 52. Okay, let me go. That's the sigma 1 which has been plotted, which has a value of 52. Yes, 52, 0. That's sigma 1. Likewise, sigma 3 I can plot, which has a value of 12, 0. Remember, both these 2 points are the principal stresses. Okay, so I'm making a statement now. Principal stresses would mean it should lie along the horizontal axis or the abscissa axis. So these two are the 2 ends of the circle. Remember, we said you can draw a Mohr circle if I have these 2 points. So these two are the 2 ends of the diameter of the circle, and knowing the 2 ends, I can find out what is the center. Half of this would give me the center. So meaning, if I take an average of sigma 1 plus sigma 3 by 2, it will give me this whole length starting from 0 to this point over here. Okay, and I can then safely draw a circle. That's my Mohr circle. Many of us are happy to draw just the upper half, and we still call it a circle. But over here I have drawn the full circle. Okay, it does not matter, because looking at a mirror image, the only difference would be the direction of shear stresses in case you look at the lower half. Otherwise, it doesn't make a difference. But if you, even if you draw half a circle, we engineers still call it a circle. Now don't ask me why, because it's a very, I would say it's a very funny situation. Half a circle, we still call it a circle. So that's the Mohr circle for us, with the two ends of the diameter sigma 1, sigma 3 being over there. Okay. Now the next part is to find out the pole, okay, which is important. So I'm not sure if I have this element over there. That's the figure over there. Okay, that's the figure. Again, the question, that's the question, the figure which has been zapped. And the part is, you do anything, before you do anything, you have to find out the pole. So for the pole, I know this is sigma 1, which has a value of 52, 0. That's a sigma 52, 0, meaning all planes which are at this angle will have normal stress 52 and shear stress 0. In other words, if I draw a line from the pole at this angle, okay, and it should hit the circle on this point, right? I repeat, if I draw a line from the pole, till now the pole is not visible on this circle, but if I draw a line from the pole at this angle, it should hit the circle at this point. This is my point over here, red, meaning, let me draw this line, let me go back, meaning this is, I know this is my end point of the line. So sorry, so if I draw a line at this angle, so I'm going to carefully draw this, trace this line. I'm going to carry this line from there and then drag it over here and trace. So I'm going to trace somewhere here, okay, somewhere here. Apologize for this rough crooked line, but what I have done is, my mouse is again moving here and there. I've drawn a line which is again at this inclination. This inclination is the same as this. So I'm going to rub this inclination off and then draw it rather clear. That's the inclination. Remember, this inclination is 20 degrees. So I have, all these are 20 degrees. So I've drawn this over there. So it hits the circle at the point P, which is the pole. So by definition of pole, if I follow the definition of pole, any line from this point P which is inclined, that means inclined at this plane, it should hit the circle which has a coordinate sigma 1 and 0. Okay, now I have deduced pole using this plane. I could have deduced pole using the other plane as well, meaning I could have drawn this lines parallel to this plane from this point which has a coordinate 12, 0, meaning that's 12, 0. If I draw a line which is parallel to this plane, it should have hit the circle at the same point P. Okay, so let's continue with the question. The question is, find out normal stress, shear stress on this plane which is inclined at alpha, and alpha is given as 35 degree, meaning from this line the alpha goes up 35 degrees. So from this line, if I draw go up, that's over here 35 degree, that's the broken line, it hits the circle at C. By virtue of the definition of pole, the coordinate of C, meaning sigma and tau, should be the normal stress and shear stress on this plane. Okay, so normal stress, shear stress would be 39 and 19. So those are the normal stress is sigma is 39, shear stress is 19 on this plane. Okay, now you could have solved this question not using trigonometry. You solved it using a trigonometry, meaning a graph paper with both vertical scale and horizontal scale of the same magnitude. It is important to have the same magnitude. That is why your circle would be uniform. Otherwise, if you somehow tweak the vertical scale or the horizontal scale different, you'll have mixed up, because your angle, your orientation will be different. So I always request everyone, all the students, that the scale of horizontal, meaning I say this much is 1 centimeter, 1 centimeter, 1 centimeter, and I say 1 centimeter is 10 kilopascal. I will say take this as 1 centimeter and take this as 1 kilopascal. Do not change sorry, 10 kilopascal, 10 kilopascal over here. Do not change the scale. Okay, so you could have solved this question using equations as well. The set of equations we have derived early on, you know, the sigma and the tau, those two you could have solved this using equation. But the next question which we have over here, it will be difficult to solve using the equation, and I request that for this figure you please go back home when we and you after the you look at the solution, try it on a graph paper with a compass and a screw ruler. Okay, please look at this question number 2 carefully. What this question 2 shows is there is a normal stress 6 megapascal in the vertical direction, and the other normal is minus 4 megapascal. So minus 4 means it's pulling the element apart, it's negative. So the arrow is outward, 6 megapascal is positive, the arrow is inward. The 2 megapascal of shear stress which acts in this direction, remember if I take a point outside, this arrow, this will give me a clockwise rotation. That is why 2 megapascal is positive. Over here, if I take a point outside, this shear stress gives me an anti-clockwise movement. That is why I have a minus 2 megapascal shear stress along the vertical planes. Okay. The question is, evaluate sigma and tau on this plane. Okay, and so on. We won't look at the remaining part of the question right now. We will look at this remaining part as we solve the question. But if I delete this thing, if I look at this figure, one quick look at the figure tells me that this 6 megapascal minus 4 megapascal are not the principal stresses, because shear stress acts on this plane. If there were no shear stresses, these two would have been the principal stresses. Right now the shear stress will act on the plane. In other words, these two are not the principal stresses. Okay, so in order to solve this, what I know from the figure is this combination 6, which is the x coordinate, and 2, which is the y coordinate, likewise minus 4 and minus 2, which is the second xy coordinate. These two act on planes which are perpendicular to each other. Okay, if two planes are perpendicular to each other, elementary geometry will tell me that these two planes should be at the two ends, or the two ends of the diameter of the circle. Okay, in other words, the two coordinates, if I go back, 6, 2 and minus 4, minus 2, these two coordinates are the two ends of the diameter of the circle. So to draw the circle, I have again a similar sigma on the x-axis or the horizontal axis, tau on the vertical axis. And if I move to next slide, these 2 points, which were 6 megapascal and 2 megapascal, that's point A, and minus 4, minus 2 megapascal, point B. We just said elementary geometry will tell us, because the two planes are at 90 degree, these 2 points are the two ends of the circle. So if I join these two, I can find out what is the center point. Center point is here. I can find out center point would be 6 plus of minus 4 by 2 and 2 plus of minus 2 by 2. That gives me a center point which is bang on the horizontal axis. Okay, if I draw a Mohr circle, that's my Mohr circle. Okay, and that's the center point. Okay, I hope this is till now, I hope this is clear to you. Okay, now the next part is we need to find out pole. Remember, any solution you need a pole. So if I go back to the question again, that was the question. We had a figure which is 6 and 2 if I look at this plane, it's a horizontal plane, and the stress on this horizontal plane are 6 and 2. Okay, the stresses are 6 and 2. So in other words, if I go back to my figure, that's 6, 2, and if I draw a horizontal plane, okay, meaning the end point of this horizontal plane hits the circle at 6, 2. So the starting point of this plane should be, by virtue of definition, this should be the pole. So that's my pole P over here, and I can read out the coordinates of P from the graph paper. I have cheated. I have before coming to class, I wrote on a graph piece of, I drew this on a graph paper, and I read out the figure, which is -4, 2. But I would like you to go back home and then deduce the coordinates. So -4, 2 is the coordinate of the pole. So once pole is found out, you can deduce stresses on any plane. So the question was, let me see, that was the question. You need to deduce a stress which is inclined at 30 degree to the horizontal direction. So meaning, if I draw a line which is shown a broken line at 30 degree to this horizontal direction, it hits the circle at a point, let me go to next slide, point C, which has a coordinate. I can read the coordinate from the graph paper. Normal stress is 1.75, shear stress is 5.35. So these normal stress and shear stress are the stress value on this plane, which is inclined at 30 degrees. Okay, so that was the first part of the question. What are the normal stress and shear stress on a plane which is inclined at 30 degrees? The next part was, what are the principal stresses? So I know this is a two-dimensional figure. Well, I can only deduce the major principal stress and the minor principal stress. I am not able to deduce the intermediate, because intermediate will have a stress value in between these two. Okay, principal stress would have shear stresses to be 0. That means I have to look at the circle which intersects the horizontal axis with no shear stress value, meaning that point over there and this point over there, these 2 points should be my major principal stress. So sigma 1 I have read out from the graph paper, 6.4 megapascal, and sigma 3, which is minus 4.4 megapascal. It's negative. So these 2 values are my principal stress values, major principal stress and the minor principal stress. The next part of the question was, what are the inclination of the principal planes? For inclination of principal planes, I only need to join the pole P to these 2 points, this pole to this point, pole to the other point. Meaning, if I go to next slide, is this broken line over there and that broken line over there. So if I deduce this or in angle, that would be my inclination of my principal plane, and if I deduce this angle, it will be the inclination of my minor principal plane. I can measure the angle the other way, meaning I can measure from there and from there. It would not matter. Okay, it's only 180 minus the other angle. Okay, the next part was, what is the maximum shear stress? So on this circle, can you guess where will be the maximum shear stress, meaning the maximum value of tau? The maximum value of tau will be at the topmost point of the circle, which is there. Okay, so I hope this can be visible. This is visible. It's topmost point over there. So this coordinate of this point will be my maximum shear stress. Okay. Okay, I hope this was clear. If you have any question, please do ask right now. The concept is fairly simple, but it's important as well, because all your strength criteria or anything to deal with Mohr circle, anything to do with failure criteria, as we will discuss right now, depends on the pole. and understanding of the Mohr circle. If you have a question, please do ask right now, or we have 5 minutes and I'll quickly wind up by introducing a simple topic. Okay, while you phrase your question, let me quickly look at failure criteria. Oh, sorry, I jumped to the next slide too quick. Let me go back. Failure. You know, as an engineer, we say our job is well done if we can draw the stress strain behavior. Okay, I see number of count going down. Number of colleges are getting disconnected. Please stay with me. This is an important concept, and it would not take more than few minutes to understand. Sigma and tau is the stress strain. So as an engineer, if you are able to predict the stress strain of a material, for example, if that is my curve, any curve, if I'm able to deduce what is my stress strain of a curve, as an engineer we say my job is over, because that's what we want. We want to know the material behavior. So the material behavior is best understood by looking at a few commonly available material. The first figure is the stress strain behavior of a mild steel. In your first year undergraduate, you would have done this, meaning you have loaded the mild steel under tension. You have applied tensile load on the mild steel and pulled the material apart. Pulling the rod would have caused an elastic deformation up to a point. So we usually call this point as the yield point, and beyond the yield point the material starts to flow in a plastic manner until it fails. So that is the breaking point. Okay, that's the breaking point over there. So you have a yield point and a breaking point, and below the yield point the material behavior is elastic. That's the first set of material. You could also have a rubber, a non-linear rubber, a material. An example of non-linear material is a rubber, meaning I load the material, it goes through one loop, unloading, it comes back to its original state, but the unloading behavior is rather different. It has an hysteresis or a loop. Okay, so these two are two different class of material. A third class of material would be, if I load the material, it undergoes plastic deformation at negligible or nearly zero strain, meaning I load the material, there is no deformation, but immediately on a certain stress value it deforms in a plastic manner. That's perfectly plastic material for us. Okay. The next one, okay, my mouse is running here and there. Okay, it's back here. The next material is a brittle material. An example of brittle material would be a glass. For example, a glass. You have a stress strain behavior which is very stiff, and beyond a point it just breaks off. The material simply collapses. Now the first four examples do not deal with soil. In fact, our soil mechanics do not deal with these four examples. Most of the theory which we follow is based on this particular example, wherein the material is elastic up to a point, up to the yield point, but after the yield point the material becomes perfectly deforms at no increase in load. There is 100% deformation, meaning can I say the material behavior is elastic up to not the yield point but a failure point. This point is now the failure. This failure point, it fails. Okay, it just fails because there is continuous deformation. So if I use this theory, I say this point is my yield point as well as the failure point. So we will look at this theory in detail the next time. Our Mohr Coulomb theory is based on this figure. It's elastic, perfectly plastic. That is our Mohr Coulomb theory. These last set of curves are a slightly complex behavior wherein the material tends to soften beyond a certain point, meaning it just goes and it has a hump and drops. even this second curve has a hump and drops. So both these two curves are called as work softening because they soften. Okay, and the other two curves, they just go on increasing. Okay, they go on increasing. So these two curves are called as work hardening material, and it means it hardens, it becomes stronger. If you happen to look at stress strain behavior of some of your soils, you will find that they tend to mimic these two examples, work hardening and work softening. Of course, these two examples are extremes and they involve some amount of complex soil behavior which we would not be able to look at next week. Next week we will look at the Mohr Coulomb in detail. Okay, so I wind up today's class. It's 11 in the morning. I hope today's class was informative. I look forward to see you again this Friday. Okay, thank you.